Okay, it's one after. I think I'll go ahead and start. My name is Barry Duggan. I'm a graduate of Georgia Tech in electrical engineering back in 1960. And at that time, they weren't teaching digital signal processing because it didn't exist back then. And let's see, what do I want to do here? Computer programmer since 1962 and ham since 1953. And my current call is KV4FV. And I've been involved with GNU Radio for about 2 years. And Derek Kozel, are you still there?
I am indeed, yes.
Why don't you introduce yourself?
Sure. So I'm Derek Kozel. I'm one of the leaders of GNU Radio along with Barry, and I've been licensed since the first year of university. And currently hold the US call K0ZEL and the British call MW0LNA. I live in Wales now.
That's great. How did you end up in Wales for your PhD?
So my wife is British, and so I moved from California here to the UK. And then, as you just said, yeah, I started doing a PhD. So I'm working on RF power amplifiers during the day.
Great. Okay, well, today I'm going to talk about frequency shift keying. And to do that, I'm going to do a screen share so that you can see what I'm talking about. And there. Oh, there I am over there. Okay. Find my way around here. Okay, this was the agenda page, and it has all the links that you may need later on. So if we go to the simulation example, gotta watch out for those tabs that are under that other thing I had. Okay, the simulation example is a frequency shift keying transmitter and receiver, and it's strictly bit oriented. We produce bits over here, and we receive bits down here. And I'll talk through these blocks, what they do. And I can give you a little bigger picture of that that's easier to read. So let's go to that one. Same diagram. We'll be there. Now, we're just going to generate some random bytes. And those are 8-bit bytes, but we need to transmit 1 bit at a time. So we're going to unpack those into 8 1-bit bytes. Now, all my orientation on this is going to be related to radio teletype, which is called RIDI. And the baud rate is 22 milliseconds, which is approximately 45 baud. So to produce that baud rate, we do a repeat. The sample rate's 48,000. So if we repeat that sample 1,056 times, we've occupied 22 milliseconds. And then there's no hardware in this whole thing, so we need to do a throttle to keep it running at our sample rate. And then we're going to do everything following in float, so we convert that to float. This pair of virtual sync and virtual source are no different than if I had taken this output and connected it to this input of the low pass filter, but it makes a cleaner diagram to do it this way. And also I need the same output down here, and that would have been real messy to draw that. The low pass filter knocks off the sharp edges of our transition so we don't produce splatter. And it's a cutoff frequency of 200 Hertz. Now let's look at this VCO. What I want is two different tones. The standard RIDI tones are 2295 for a 1, a mark, and 2125 for a space. So to make the VCO generate that, I chose a full scale frequency of 2500 Hertz. Could have chosen anything, but that was a nice figure. So to get the space frequency of, okay, first the sensitivity is in radians, so it's 2 pi times the 2500 over an input of 1 gives me that 15,000. So to get a space, I take the fraction of that, 2125 divided by 2500. So I need an input of 0.85. So when I have a 0, I want 0.85 going into the VCO. So to get a mark, I need to get the ratio of 2295 over 2500. So I need to add 0.068 to give me a total of 0.918. So here's what I did. I multiplied that input, which is either 1 or 0, by 0.068, added 0.85, and run that into the VCO. Since I'm full screen, I don't have any feedback. So if someone wants to ask a question, I will address that. Right now, I'm not hearing anything, which is a little disconcerting. I don't even hear myself in my headphones.
Yeah, it's okay.
Okay. So that's the end of the transmit side. Now I'm going to receive it. So I take that FSK output and I downshift it. Going into this, the frequencies were 2295 and 2125 with a center of 2210. So I downshift it so that those tones are centered at 2210 in the baseband. So anything above 2210 is a positive frequency. Anything below 2210 is a negative frequency.
Barry?
Yes.
Can I ask a question if that's okay?
Sure.
So hopefully, from my inexperience here, what's the bandwidth that's generated with RTTY? So is the 15,000 the actual bandwidth of the signal, or the bandwidth isn't around 2500?
The actual frequency deviation is only 170 Hertz.
Okay. And then you're switching between the two frequencies.
Right.
Okay, got it.
So as long as we have softened those switching points, we don't generate a very wide band spectrum.
And so the 15,000, go ahead if you're okay.
You're referring to the low pass here?
No, choosing the full scale frequency of 2500, the VCO max with an input of +1, the VCO sensitivity is 2 times pi times 2500 over 1, which is 15,708.
Right.
So that's
why did I choose 2500?
Yeah.
It had to be something greater than 2295.
Okay.
And because that gave me 0.918, using the 2500. If I had chosen a larger frequency, it would have given me a smaller input, but also less variation between the mark and a space. So I figured I'd
Okay.
get the best accuracy out of the VCO by
Okay.
choosing a scale not much larger than what I needed.
Is this typical for RTTY from like the commercial systems, or is it?
The 2295 mark and the 2125 space are standardized pretty much worldwide.
Okay.
And the only
Okay.
variation, which I'll get back to in a little bit, is which tone is mark and which tone is space. But we'll look at that in a minute.
Okay. Thank you.
Yeah. So we have a baseband here with the two frequencies split between a positive frequency and a negative frequency. The squelch we really don't need until we get on the air, but for consistency, I go ahead and put it in here. So the quadrature demod will produce a positive output if the frequency is above 0, and a negative output if the frequency is below 0. Remember, we're in the complex domain here. So that we get a plus something or other out for a mark and a minus something or other out for a space. So when we run that into a binary slicer, it produces a 1 if the input is above 0, and a 0 if the input is 0 or negative. So now we're back to the bits that we generated up here in this first line. And converting that to float, we have the same signal as what we transmitted. And I've pulled that down here. Now, if we were to just compare the two, they wouldn't match because there is a delay in the processing of all of these blocks through the filter and the VCO and another filter and so forth. So we have to introduce a delay in the transmit signal if we want to try to match it to the receive signal. And it turns out that delay is 202. So if you run the simulation yourself, you'll see that. I think I will move on. I would have run it if I had been a little quicker in that first part, but I think I'll proceed with the next phase. And we'll be going through these blocks again a little more hurriedly here in a minute. So, okay, to review, this is just bits in, bits out. There's no word orientation, and we did not reassemble this byte up here from the random source. So this is just a bit string. Now, when we look at a real world use of this, where we apply it to Bodo, I think is the correct pronunciation of Emil's name. He's the one who created that. I'm going to take a message in and I'm going to convert it from UTF-8 to Bodo, which is a 5-bit character, a start. So that the whole thing is 1 start bit, 5 data bits, and 1 or more stop bits. And when I say 1 or more stop bits, it can be 1, 1.5, which is only used in some old machines, and 2, which is the most common, or it can be semi-infinite because it is totally asynchronous, character at a time. And I run that into, we're still at 48,000 sample rate. So I have the same repeat here to get the 22 millisecond and change that to float. I'll go ahead and do this and then come back to this conversion here. So it's the same filter to smooth the edges, the same VCO setup to get the two tones, and then output to an audio sync. And then I also have a scope trace here that'll look at the tones and the data. Now going back to this, this is actually a Python, embedded Python program. And let me, right here. This is actually available in the links to my package. So I have a table of all of the, let's see, can I move that over a little bit here, of all of the Bodo character set. And so I take the text in, look it up in the table, generate the correct Bodo code, and then serialize it and put it out as a vector. So that's what's happening there. Okay, now on the receive side, I'm doing the same. Let's see. I guess you folks are seeing me here superimposed on this diagram, aren't you? So let me see if I can move that over a little bit.
No, it's okay.
How. Okay. Okay, so it's the same chain for the receive. We've got the fur filter that's doing the same, translating the tones down centered on 2210. And I'll come back to that decimation in just a second. Here's my squelch, here's the demod. So now let me talk about the decimation. We came in at 48,000 sample rate, and I'm going to decimate that by 50. That means divide it by 50, which gives me a sample rate coming out of here of 960. And then run that through the quadrature demod into another resampler, which the resampler does both interpolation and decimation, so you can adjust your sample rate to whatever you want. Well, if we decimate by 960 and interpolate by 500, we get a sample rate of 500, which is exactly 11 samples per bit, which is why I chose the 500. If I had used some other sample rate, I would have had a not an exact determinant of how many, where the bit boundaries were, is what I'm trying to say. But by going to 500 samples per second, I have 11 samples in 22 milliseconds. And that's what I was achieving at this point. So then I'm going to tell you what, I'll pull this down. Yeah, there we go. So coming out of here, I've got 11 samples per symbol time is the correct terminology for the Bodo. And here's what I was saying, sometimes the mark and space frequencies are inverted. If you're on 40 meters or below in the US, I guess worldwide, you use lower sideband, and that inverts the frequencies. So all of a sudden, mark is the 21/23 5 and the space is the 2295. So I needed a switch to be able to go back and forth between the two. And so I did a GUI chooser with a multiply of 1 or -1 to do that inversion. And then coming across here, we've got the same binary slicer. And then a terminal display sync is another embedded Python block. And it's right up here. So it reads the stream of 1s and 0s. There are 11 samples for every bit time. So this is basically a software UART. I'm synchronizing on the start bit. I'm doing majority voting on whether that bit is a 1 or a 0. I think I'm using 7 out of the 11 bits to decide whether it's a 1 or a 0. And then I gather the 5 data bits and I convert it to UTF-8. And as soon as I've gotten a good stop bit, I go back to looking for a start bit. So that's why it will take the 1 stop bit, the 1.5 stop bits, 2 stop bits, 3, 4 infinity stop bits, because it's searching for another start. Okay, let me go back here. And then I spit that out to a CMQ message sync. So now let me look at the overall plan here.
Barry, is it possible I can
Yes.
ask another question?
Yes.
Back to your Python code, is that sort of like a walking window technique for your start and stop bits?
It is, yeah, there is a, if you go to my, let's see, where are we here? Yeah, if you go to my page where you got the,
Oh, it's okay.
anyway, on the page where you got the link to join this meeting,
Yeah.
there is a link to GNU Radio Basics. It's a GitHub. In that package is that code for the sending and receiving, the code conversion.
Yeah, I have it in front of me here. Okay.
Okay.
Okay,
So,
thanks.
So these files, FE block 00 and FE block 0, are in the transmit and receive portions of that GitHub. Okay.
Yeah. Okay, thanks.
Okay. Now, next thing I want to do is do a loopback to show you that this really works. So we're going to, here's the transmit coming to an audio output jack. Going to patch that into the receive that has an audio input jack. And then we're going to send the text to this GR web server, which is a terminal emulation program I wrote. It is web-based and it's written in Node.js. And you'll see it here in just a minute. So anyway, received text gets displayed, sent text gets displayed as well, and sent to really transmit. So let's go ahead and set that up. I've got a cheat sheet here in front of me. So that's going to be 3 processes there: the transmit, receive, and the web server. So I'm going to open a window, and I have shortcuts here. Save me a lot of typing and avoiding mistyping. So here's my transmit scope screen. Like that. And then I'll open another window and I'll do the web server. And this, like I say, it's browser based. This is just another tab in Firefox in my case here. So whatever I type in this input box, one line at a time, as soon as you hit return, it gets sent to the transmit side. And you'll see this in action in a minute. So we need to start the receiver. And 20. And there's my receive window. And my noise is way down here below 100, minus 120 dB, because it's just a straight cable. Now here's my reverse switch, normal or reverse push buttons. So let me get some text and the tradition is quick bound Fox, which if you're not familiar with it, contains every letter in the alphabet. And by the time we finish with the figures, we'll have every figure in the Bodo character set. So I will copy that, go back here and paste it to my input. Now, I'll show you three things here. First of all, when I hit return or enter, whatever you like to call it, it will be displayed here with a greater than sign in front of it, which means it's outgoing. And then when I get an answer back, it will be displayed under that with a less than, meaning it's incoming. So let me hit this, and there's that. And then there's my transmit, and that's the tones in red and the data in blue. And then the receive, I didn't catch it in time. We'll get that next go around. On the receive side, oops. My microphone. I was having little microphone problems this morning with it switching between the camera mic so you can hear and the audio jack for. That's probably what I need to do. Sorry for the delay here. I don't see a microphone here. Oh, phooey. Well, I may just move on to the on-the-air demo because it uses different input. So let's do that. Anyway, on the web server here, any received data would come in here and display. Let me just check real quick here. There's outgoing. No joy on the input. So let me just move on here. Stop that. And close that. And close that. And close that. And close these terminals as well, because sometimes I have stuff hanging around we don't want to hang around. Okay, so the next phase of this demo is to do an on-the-air demo. So we're going to use a different transmit that feeds into a USRP, a B200 mini over-the-air radio signal into a Pluto receiver in the Raspberry Pi with the same receive program. It's actually an audio link across here and back into the web server. So somebody talk to me and tell me that we're still good.
All good.
Okay,
All good. We can hear you. We're still alive.
Like I say, there I hear nothing unless one of you speaks. So
we're in absolute awe. No, it's going well.
Okay, as in all live demos, even though you pre-test it, it doesn't always do what you want it to do when you go
So basically,
live.
you're just transmitting across the room type of scenario, right?
Actually, it's about 6 inches away from the transmitter and receiver.
Okay.
But,
so the path loss isn't that great.
no, but I'm also in the milliwatt power range here. So, but anyway, let me see if my screen will work over here for the Raspberry Pi.
It would be interesting offline
Yeah,
if,
there we go.
do you have a transmitter onto a HF antenna? Are you in the States? You could try to transmit and I could try to see if I can get you in
I don't
Canada.
think you'd receive me on 2 or 3 milliwatts.
Well, I was just saying if you had a 100-watt transmitter or something.
Yeah,
But anyway,
right.
Yeah.
That's next week.
Yeah, exactly.
Okay.
That's offline.
Okay, let me see if I can move myself down here. Way down here in the corner. Yeah, that'll help. Okay, what you're seeing is the screen on the Raspberry Pi. And the magic to do this is through VNC. But sometimes you'll see this pause a little bit. And the reason for that is the VNC client on the Ubuntu would not talk to the Raspberry Pi, but it would talk to my Mac, and my Mac would talk to the Raspberry Pi. So we're actually relaying this picture from the Ubuntu to the Mac to the Raspberry Pi. Fun and games. So what I'm going to do now is I've already got the radio part of the receiver running over here. I'm going to start the RIDI receive program. And just to be safe, I'm going to do it on the keyboard of the Raspberry Pi instead of 19 or 20. Takes a minute to come up. Okay, and there's my receive. So let me move those over where you can see them better. That's the receive. There's my squelch that I'm really using this time since it's on the air. My normal reverse switch. And I have more noise now because this is really receiving signal. So I'm up to minus 80 over here. And then on the receiver here, there's my spectrum. And I'm using 144.95 as the frequency. So there's the receive side. So let me now go back to the Lenovo, which is running the Ubuntu 20.04. And what do I want to do here? Yeah. Okay, I want to start two processes. Back to my cheat sheet. Okay, let's see. I think we have time. First thing you do when you're receiving ready is to get it tuned in. So I actually wrote a program to transmit the letters character, and then I will tune the receiver to get that where it needs to be. So let me do that. And I will add that to the GR Ready Basics package next week. It's not there yet, but the transmit is. Okay, letters. So I am now transmitting the letters character, which is just a start bit, and the rest are ones. So 5 ones plus the stop, which is another one, and 2 stops, which is 2 more ones. Yeah. Okay, and give it a little, give it a little more gain there. Okay, now let me go back to this screen share, or I mean the Raspberry Pi screen. And you see this white line up here in the middle of the spectrum. That is my, there it is. That is my signal being transmitted. And you see down here in the receive, that's my spike for the mark frequency. And I'd like to get that up a little higher. So I'm going to do some tuning. And I'm going to bring that, let's see. We'll get it closer. That's pretty good. Okay, so I adjusted the BFO. Okay, let me get that where you can see it better. I adjusted the BFO to where I got my signal on the receiver down about 2300. Okay, so that's how I've got it tuned in. So let me go back to the demo here. Okay, on the transmit, I want to stop transmitting. And instead, yeah, make sure I'm where I think I am. I want to do an actual so there's my transmitter window on the Ubuntu. And then I need to start GR web server again. But this time, instead of listening to the local receiver, I'm going to listen to the Raspberry Pi, which has a different IP address. So that's that one. So now let me see if luck is with us here. Sometimes when you're tuning, you'll pick up there. Hey, great. Sometimes when you're tuning, you'll pick up garbage, which you don't see until you get a carriage return. So I'm sending out some traditional ready separator signals, like sort of the beginning a message kind of thing. So we're going good here, and I'll show you all the action as we go along. Yeah, we're okay on time. Okay, we're back to Quick Brown Fox. So let me copy that again and paste that in here. Okay, and I'll try to show you three things that is happening concurrently. Okay, that's the, and here's the outgoing signal. You can see it's actually running that stuff. And then here's the receive. You see the white band is the signal going out, and down here was the receive showing the mark and space frequencies. And then if we go here, sometimes we'll pick up a little garbage character, but there's the Quick Brown Fox. So now let me do figures. There's Bodo, since it's only 5 bits, you can do the alphabet and a little bit more, but to get figures, they decided to use a letters, figures, 2 shift characters, shift to letters, shift to figures, figures being all this special stuff. So anytime the code encounters, well, it starts in letters. So right here, the apostrophe after dog, it had to do a figure shift and the apostrophe, and then a letter shift, and then the S. So here I'm going to do the remaining figures. Here's the transmit, and here's the receive. You can see the peaks there. And there's the return text. And since I'm on the air, I better send a station ID. So let me do that. Don't want the FCC after me.
I don't think they'll be after you at this power level.
No. Well, I have actually transmitted from my office here to the kitchen, which is on the other end of the house, about 60 feet or something like that. And that's as far as I've tried to test it. But that was with an old laptop, which has since crashed. So I couldn't do that test today. In fact, I was thinking about having someone in the kitchen on a full working setup. So instead of getting echoes back, I'd get whatever they typed, which would be even more fascinating. So that is the, are there any questions before I turn off screen sharing?
I do have one quick one, if that's okay.
Sure.
Mike here again. That's very, very interesting that you did the GR web server. That's very cool. So theoretically, as it currently stands, if I had an internet connection to your house, I could go in, write the software, and then I can get your output texted to my web browser from your receiver. Theoretically, if I were to connect to your through your house router and stuff. Is that, do you understand what I'm asking?
Yes, that is correct. This link right here from the
Yes.
web server to the transmitter is IP link, but it's local on this side, but it doesn't have to be local. And what I'm doing here on this side is using the IP addresses of the Raspberry Pi and the Ubuntu. And so you know, once it's in that form, these sockets can be anywhere in the world if you had the IP linkage for it.
Yeah, going through the router.
Yeah.
So that's very interesting. So someone like me or whoever in the world can transmit on your computer and hear it theoretically if you're going out on the air 100 watts, and then receive it and vice versa.
Right.
Yeah. That's quite interesting. That's cool.
Yeah. Or I could send you the text on this link.
Yeah.
And you could receive it.
That's right.
On this link.
Yeah.
And see what I'm sending.
Exactly. Yeah. No, that's
so
cool.
a lot of possibilities there.
Yeah. No, that's very good. It's very good.
And of course, if you have a traditional sideband rig, you just plug the audio into your sideband rig instead of loopback.
Exactly. Yeah.
It's ready to go.
No, that's really cool. It's well done. Very well done.
Thank you. Okay. Oh, we got a latecomer here. Greetings to the one that just came in. We are recording this, so what you missed, which is most of it, will be put up on YouTube as soon as Derek can take care of that. So I'm going to stop the screen sharing so that I can see people again here. It's scary. Let me do a gallery view so I'm not staring at myself in such full screen glory. Okay, at this point, if there are no more technical questions on the presentation, I'd like to discuss, do you like this whole deal of having these video meetings with presentations? How often should we do it? And as many as you want, either do it on your camera or over here on chat, and let's see what you have to say. So my first question was, do you like doing it once a month or whatever?
Yeah, I think the interval we had between this and the last meeting was pretty good.
Well, that was 3 weeks, but that's because this was a repeat.
Oh, okay. Okay.
And of course, we're staring at the holidays, which is my next question. Should we skip the holidays and just go to January for the next one? You think that's probably best?
I don't know. I see no reason to skip. Nobody's going on holidays anyway. Just talk at home.
Yeah, we got Thanksgiving and then the Christmas or whatever other celebration people make around that time.
We might actually have more time to play.
Hadn't thought of that. If my plans work out, I'll be at the beach over the Christmas and New Year's, but I'll have my computer with me. I guess there's no reason I couldn't do something from there. And then I don't think Michelle Thompson made it this morning. She was going to try to, but she had volunteered to do one on the FCC rulings on amateur satellite communications, and then talk more about amateur satellite in general. And I haven't gotten feedback from her. And a couple of others have indicated some possible programs like FreeDV, and I think there were some others. Anyway, I need volunteers. I don't anticipate hosting or providing demos on a continuing basis. I'll certainly be a participant. Yeah, Adrian, go ahead.
Sorry, yeah, so I think I have something to present as well. I can present it today really short if there's enough time remaining in the meeting. I don't know if the screen sharing will work because for me the whole meeting has been black screen. I'm using the browser and not the Zoom application. So I hope it would work. And if you have time now, if not next week, or next time, it's fine for me.
According to schedule, we only have 7 minutes, so I think we ought to.
The Zoom call will stay open, or can stay open. So
okay,
we don't mind running a little long. What do you have, Adrian?
Yeah, so there's just some recent things I've been working on this week. Basically, video transmission with the GNU Radio. It's something that I had been working for some time, at least 2 years, but now the video also has sound, so it's more user-friendly. You can actually hear the person talking.
Cool. Did you have any other questions, Barry?
Oh, is that you? Yeah.
Adrian is already
yeah,
sharing.
just the basic, trying to plan another meeting and how we go about it. Mm-hmm. So is this Adrian's screen we're seeing here?
It is, yes.
Yeah, so just let me switch the audio. You will not be hearing me for a couple moments because I will switch audio to the receiver, and then you'll hopefully hear me over the radio. So the transceiver is in loopback mode. It's working duplex. So it's duplex operation and it's loopback. The antennas are like 10 centimeters away from one another. So it's just very low power. I'll just switch the audio to, if it will allow me. I hope it allows me to switch the audio, but
Adrian, I think you need to change it in Zoom itself. I had the same issue just before. You need to change in Zoom. You cannot change it via the view control. What is it called?
Yeah.
So if you go to in Zoom your audio setting, and there you can change your no, on top the microphone. I think you need to change your microphone. And you need to change your correct.
It's just that.
I don't hear anything. I know. Supposed to.
No, I don't either.
Yeah, there's indeed a loopback.
I should probably put out an ID then. This is MW0LNA.
Aiden, I don't know if you are transmitting, but we do not hear you. There's a very nice echo.
So hopefully you can hear me now.
Yes.
Okay. So yeah, because apparently Zoom in the browser has some issues with Pulse audio, I will just disregard the sound and just show you how this works. So I've implemented the video transmission in GNU Radio with sound as well now. So it's no longer just like silent movies of the 80s thing. The video is quite low resolution because I try to keep the bandwidth usage low. So this is the video signal being transmitted here. There is also a constellation display where you can monitor the signal quality. So if I increase the gain, you can see that the signal becomes suddenly a lot more readable here. Right now, the way the video works is it captures the video from the camera, then creates some frames. They are encoded in JPEG format. Also adds the audio frames, which have the sound. Okay, so this is the radio timeout. It's warning me because I have a timeout set at 2 minutes for the transmission. The video frames will be transmitted together with the audio frames. The flow graph is just a very basic differential QPSK modulation. It's single carrier, so it's not OFDM, it's just single carrier differential QPSK modulation. And it's got convolutional encoding and decoding forward error correction in the signal. As you can see, the signal is about 350, 325 kilohertz wide. So this is something I'm working on for the Quebec Oscar 100 amateur radio satellite, which we can use here in Europe. And I hope that with my limited antenna and the limited output power from the transceiver, I'll manage to do some video QSOs with other hams we can access the satellite. Yeah, so sorry for the quality. The quality is basically there's some light going right into my camera because this is it's not really good quality video, but I think it's just about enough to say that you're actually transmitting video over the air. But this is a code that I recently committed just this week. So it's I've switched the video backend from video for Linux 2 to use the Qt video backend, which under the hood uses the GStreamer plugins. So there are some issues. The GStreamer's plugin is bad, library is needed, and there are still some issues. Probably that's why it's called GStreamer plugin is bad. There are still some issues left, so I'll be working, hoping until Christmas I'll be able to get something quite stable that doesn't randomly crash or something like that. But yeah, so this is what I wanted to show. Like I said, I wanted to make it really, really short and just show you how this works. So video, transmitting video and also audio. You will notice that if I stop transmitting, the window will be gone, so it will no longer show. And if I start transmitting, yeah, by the way, this is something I wanted to ask. Sometimes, apparently, on very high symbol rates, the Costas loop seems to lock onto the wrong phase angle. So I've tried asking for advice on the general channel, but I don't know why is this happening. It should be slicing at 45 degrees, but sometimes it doesn't work. If I restart the flow graph, it usually comes back normal. So I think this is it. I don't want to take any more of your time. The latest news from me, let's say. Thank you.
Well, thanks a lot, Adrian. And actually, just can you talk briefly about Q Radio Link and what it is as an application? Because I suspect that some people here won't have seen it before and won't realize that it's using GNU Radio entirely on the core.
Yeah. Sorry, I forgot to introduce myself. So my name is Adrian. I'm from Romania. My call sign is Yankee Oscar 8, Romeo Zulu Zulu. I've been using GNU Radio since 2006, just as a user. So I didn't actually write a lot of code with GNU Radio, but I've been using it for experiments in this period of time. So while I was doing that, I saw the very nice software by Alex Chete, Oscar Zulu 9 Alpha Echo Charlie, which is GQRX. And it was using the GNU Radio API under the hood. So around, I think 2016, I started to try to work on a full transceiver because GQRX is receiver only. So inspired by the features in GQRX, I tried to build something quite similar. It's based on Qt, so the whole interface is basically Qt. It's Linux only, so unfortunately you won't be able to use it on other operating systems because I'm a Linux only user since a long time, and I honestly don't know how to program under Windows or other Mac or FreeBSD. I've never used them, so it's Linux only right now. So yeah, it's using GNU Radio under the hood for all the digital software processing. So there are GNU Radio flow graphs. They're written in C++. Just as an example, so this is like the way that the flow graphs look like. They're written in C++. That's not because I don't like Python. I'm actually a Python developer myself, but I kind of hate Sweep, and I find it a lot easier to just call the C++ API directly and link against it. And this is what QRadio Link is doing. It's got a bunch of C++ code organized into flow graphs. There are a bunch of digital modes which I use for experimenting myself, like frequency shifting to FSK, respectively for FSK. Also BPSK, binary PSK, and FreeDV, but I'll let the mate talk about FreeDV because it's really his baby. There are some other demodulators and modulators like narrowband FM. This is what I've been actually using the most in the last year or so because we have a lot of FM repeaters here, and I access them remotely using QRadio Link. QRadio Link can also connect to voice over IP server, which uses Mumble, and can forward the audio to the Mumble server, and then from the Mumble, so the architecture of the Mumble server, UMurmur, the way it's called, it's a hub and spoke architecture. It allows any number of clients to connect with, and it's obviously full duplex. So if you have like, let's say a bunch of SDR based nodes, you can, so whatever is received on one SDR, it will be forwarded to all the other nodes, which will appear as users here in the channel. So let me just, I'll open the actual Mumble. So this is what the Mumble client. Mumble is a very well-known software used for voice chat. It's actually very good, and the protocol is extremely well documented. So this is why I've used it. So yeah, so this is what I was talking about. You see a lot of issues with the GStreamer plugins. Okay.
Adrian,
Yeah.
I have a question if that's okay. Hello?
Yeah. Yeah. Can you hear me?
Yeah, can you hear me?
Yes.
I'm just curious, which SDR are you using?
So here I have quite a number of SDRs. So I started by using a couple of USRPs. I had a B200 and a B205 Mini. But that was when I was located in Ireland. So here in Romania, unfortunately, you cannot just buy them using the credit card. I think they're restricted for export or something. So when I came back to Romania, I got a couple of other devices. Currently, I'm using to transmit. I'm using a LimeNet Micro. It's a device which is quite similar to Lime SDR Mini, but it's also got an embedded Raspberry Pi module. I'm also a user of the Lime SDR Mini. I have a couple of them here lying around. Mainly lately, I think my main driver has been the Pluto SDR. So I have a couple of Pluto SDRs here. I use them because they're cheap, and I can give them to fellow radio hams, local guys here, and let them test them. So that's my main driver. But I also have a couple of other devices, Lime SDRs basically. The USRPs I gave them to what's it called? It's one of those hacker clubs where they experiment with stuff. I wasn't using them at full. They're very capable, and I wasn't really using them fully. So I gave them away. I only have the Lime SDRs now and the Pluto SDRs.
Okay, thank you very much.
Adrian, a question. Is that the television mode that's now used on Q100, which is narrowband, I think, what is it called? NBTV or something?
No.
Reduced band
It's
TV?
That's something that I didn't really have time to look into. So I'm like in the last year I've written very little code. I'm quite busy with work and this whole pandemic situation. So I've had to limit my involvement with the code. I haven't looked at that. This is something that I came up with maybe 2 years ago. It's something that I use for experimentation and with a couple of other hams here on the higher frequencies, 1.2 gigahertz and 2.4 gigahertz.
Okay.
Yeah,
Because not
so
just because you mentioned Q100, I know they use something called the.
yes, I plan to actually look into other video modes. I just don't know what's the status of the support in GNU Radio, because I am reluctant to use other DSP libraries other than GNU Radio, because I simply am very familiar with the GNU Radio. So that's why I tend to use anything that's GNU Radio based. Maybe also in the future there are some very nice modules from RON, W6 RZ for DVDS transmission. I plan to look into that when I have time. Also, something else that I wanted to mention. So there's you're not gonna do much unless you can use higher power. So you're not gonna get very far with these small SDR devices. So what I've done, I've implemented support for some USB relays. They're based on the chip FT232 from FTDI. So if I click here on enable relays, and then I've basically just enabled relays, and then there's another setting here, and I can select which relays to toggle. So my setup here is basically the SDR relays. I have some transmit receive switches which are controlled by the relays, and some amplifiers and filters, of course, for every particular band. There's an interesting device which is maybe expected to come up. It's called the Lime RFE. it should do pretty much the same thing, except that I have some higher power amplifiers here. My playground is generally 2 meters and above, into microwave, and I use up to maybe 50 watts on these frequencies.
Okay, thank you.
Can I ask a question or a comment, Adrian, if that's okay?
Yeah, sure.
Have you heard of the BATC, the ports down transmitter?
Yes, I've heard of it. I haven't had a lot of time to play with it because I haven't figured out how to control the transmit receive sequence. So my time is is really quite limited. I think most of the time I'm just chatting up with people here on repeaters and stuff like that, and maybe once every 2 months I get some weekends to experiment with new stuff. But the ports down transmitter, I'm planning to try that on the Quebec Oscar 100 satellite as soon as I can. As soon as I can get.
You guys are lucky.
So Adrian, good news. I've tested the GNU Radio DVB blocks against a ports down transmitter. And so if you can find all the right settings, they are compatible.
Yeah, that's cool.
Yeah.
And now we just need a fast internet from Canada up to somewhere in Europe so you can go upstream.
Cardiff University volunteers.
Well, we have pretty good fiber network in Canada, so. Oh, Barry's back. Hi, Barry.
Okay, I have moved some cables around, and the demo I did 3 weeks ago, I actually had to move cables during the demo and thought I had fixed it where I didn't need to today. But what I'm going to try to do here, let's see what I have running. I still have if y'all want to hang with me, I'm going to go back and close down get back to my starting point here. I'm going back to this audio loopback, except I'm actually using the receive in the Raspberry Pi. So my patch cable goes from the output jack of the Lenovo down to the input jack of the Raspberry Pi now. And everything, if the stars line up, I should get get it to work this time. Oh, one other thing that just came to mind, there's actually, if you're interested in radio teletype, there's actually a news service that runs around the clock on the internet where you can go to it and plug that audio into your receiver. And so basically you're running that path from the your audio output of your computer into the RIDI receive program and then into the web server. And I'll give that link here in a minute. So let me, what am I doing here? Got to figure out what I'm doing here. Oh, okay, for loopback I need, oh, let me go back to screen sharing. That would help. Yeah, okay. Now I'm going to go back to my transmit. I'm sure glad I didn't have to type all these commands. So there's my RIDI VCO, which is the audio transmit side. And an audio patch cable going down to receive running in the Raspberry Pi. So let me start the web server. Okay. Now see, I can actually go back and make corrections here until I hit the enter key. Oops.
We can hear the tones in the background.
Oh, you can't hear that? Okay. Oh, I started the wrong one here. Let me fix that. My yeah. I use the local IP addresses and not the others. Yeah, 22. Yeah, there's my hello. So along with a little garbage to start. Yeah, can you hear those tones?
Yeah, we can hear them.
Okay, that's what RIDI sounds like. So let's go back to the QBF, which is the shorthand for quick bound box.
That's funny.
And there's the transmit. And that's the tones, and that's the data is in blue. And there's the receive side.
So this is through the audio or over the air again?
This is the audio loopback.
Right.
It
Got it.
didn't work the first time around.
Got it. Got it.
So maybe Derek can patch this in when he builds the video for the YouTube.
Yeah, cut and paste, no problem.
So you want me to do one more time and show you the screen on the Raspberry Pi?
I can use the screen from the Raspberry Pi before, I think. That should
Oh, yeah, right.
be fine.
Okay. Well, this doesn't use the radio receiver this time. It's only using the RIDI receive part.
Barry,
Yeah.
do we have time? Are you able to go into your filter a little bit? I'm just curious what your bandpass is and more details on the actual filter, if we have time.
Okay. Sure. You talking about on transmit or receive or? which
Receive
side?
would be the receive more so that I can
Okay.
understand.
Okay. Okay, the audio coming in, as you heard, is the two tones of 2295 and 2125. And this frequently translating per filter, it's a tongue twister, downshifts that spectrum, centers it on 2210, which is halfway between those two tones.
Okay. So what would be the pass band then?
Okay, well, keep in mind it's only 170 hertz between the two tones. So
Okay.
the low pass filter, I'm screen sharing, there it is. So it's float to complex with real taps, and the filter, which I also list on that a tutorial. Gain of 1 at the sample rate, audio passband of 1,000 hertz, and a roll off of 400.
Okay. Okay, got it. Got it.
I do have a question. Sorry.
No, that's good. Thank you.
Okay.
Is my audio on here? I have a question. I've never seen the frequency translating block actually that takes floats to complex, because I usually have something that takes complex to complex. Does it
Well,
mean actually
you have choices for whichever you want.
yeah, but
So you've got the whole range here.
that means it needs to first do some conversion going from float to complex, which probably means that you throw away 1/3 of your bandwidth. Is that the trick that they do? I don't know, somebody who's more DSP knowledge.
Well, you're throwing away negative frequencies, but incoming, all you've got is audio, which is
Well, I understand. So
in
you start with
floats.
something that has frequency 0 to 24 kilohertz on only the positive side, and then he converts it for, I think, first to complex, and then does the downshifting. Or am I wrong here?
You're asking which happens first.
I don't know. I don't know who actually wrote this block, but the first time the first time I see this block X taking floats as input and not complex.
Okay, let me show you what I do. I'm still in screen share here. Okay.
No, I do understand. I mean, that's.
I'd go to category block docs. I hope you were familiar with those. And then I'd go to frequency translating FIR filter, which is right here. And it has a really nice explanation of translating from the input to the output.
But that block starts with a complex. If you look at the graph, it starts with something that's complex, because you see it's not symmetric.
You're talking about my flow graph?
No. The drawing you see on that page.
Oh, right.
It starts with something that's complex because it's not symmetric on 0, so it's complex already.
Right, but the audio would just be the positive frequencies.
Okay.
And so just like the orange is here, we're going to shift that down so that the two RTTY frequencies are plus and minus, with the center frequency of 2210 in the middle there.
Yeah,
and so that's what we want.
Oh, I see. So this X-lating FIR filter is combining all these into one block. Is
right.
That what I'm understanding?
It's doing three things for us.
Okay.
It's translating the frequencies. It's filtering so that we just get what we want here with the anti-aliasing.
Okay.
And then it's decimating for me, because I wanted that too, because I'm decimating by 50 in this case, going from 48,000 sample rate down to 960 sample rate.
Okay.
So it's a multifunctional block there.
So if you go back to the page for a sec, maybe I should do that, look on my own. When you go down the decimation, it's above and below 0 hertz, I guess, is that? And then if you need to shift it up, then you just say, okay, move your, yeah, I'll read up on it. Okay. But that's good, thank you.
Yeah, so coming out of the output of that filter, it is, well, like this drawing shows, it's decimated and it's centered at the center frequency of the RTTY tones, but it's also converted to complex because I guess it could all be done in float. Well, no, the quadrature DMOD has to be in complex. That's why I did that. it needs the plus and minus frequencies as inputs. So I needed to get that out of the FIR filter and into the DMOD. And then its output is back to float. You can let's see, what do I want to do here? Okay, here's my GitHub page. So you've got ready receive and ready transmit. So if you went here, you've got the flow graph, you've got the Python, you've got a picture of it, and there's the embedded Python code that I showed you right there. So it's all yours for the playing with, and feel free to fork it and make modifications if you like. One of the things that people have talked about doing is, let's see, I'll stop the sharing now. Yeah. One of the things people have talked about doing is putting in some tuning mechanism to automatically tune into those frequencies, sort of like an automatic frequency control. And that would be an interesting project, but I haven't had the time to do that yet.
I still have a question. So
Yes.
do we still have time? I also did an RTTY decoder, I did a demo on that, and the codes I found, or the drawing I found, actually uses a block recovery block, a clock recovery block, because in your case, you do the synchronization of where does my Bodo sign starts in your Python code. There seems to be blocks like the clock recovery, which seems to be able to do that magically.
But it only recovers symbols.
Yes. So we give it, you have the omega, which means how many symbols you have on per sample. And for some reason, it seems to be able to, well, magically do itself. So I don't know what is the best to do. Use these magical blocks that seems to do everything for you, or?
I don't think the magical blocks are going to recover the bytes. It's going to give you a bit stream that's synchronized to the clock, but you still have to do this async UART function to
but you need to find your start and stop bit. Okay, but apart from that, you need to know where your bit starts in your data samples, because in your case, what you're doing, you get sample per sample that actually goes into your Python code, and then you need to find yourself where does the start bit start. Am I correct? Or you?
You're right.
I think that's what the Python code is doing.
Yeah, it is a software UART, and if you're not familiar with that term,
I know what it is. That's not
okay. So it's a software UART. GNU Radio does not have a UART function.
Yeah, but the question here is
on bits,
how do you
streams.
How do you determine if where actually your start bit starts in your samples stream that comes in? That happens in your Python code, I guess.
Yes. Yes,
and
exactly.
The clock recovery block seems to do that by itself. So I don't know what actually is the best choice to use. The problem with the clock recovery block, you have except one parameter, which is the number of samples per symbol, which I understand. There are 4 other parameters. I have no idea what they're doing. So that's a bit the problem with those magical blocks, that they have a lot of parameters that, well, are magic, I guess.
Yeah.
Well, if you use one of the GR blocks, you're going to find some 0 bits going through the data, but how do you know which one is the start bit? So I don't know of any GR blocks that will
That's
pick
part.
out.
That's part two, I think. First, you need to know where your bit actually starts in your samples, your audio samples, and then from there I need to find where does actually my Bodo character starts.
Yeah, well,
But that's the second step. But the first step for that, I found this clock recovery block, the clock recovery MM. There are probably 3 or 4 of them, and I have no idea what actually they do and which one is best, and if it is a good idea to use them, yes or no. I think Adrian wanted to say something.
Yeah, it is the clock recovery MM is something that I use as well everywhere. So anywhere you have more than one sample per symbol, you basically have to use the clock recovery block. And I think right now in GNU Radio after version 3.8, there's a better clock recovery block called this symbol synchronizer block, which should practically accommodate all the algorithms which are included in older versions of GNU Radio. So it's for phase modulated signals, it's the polyphase clock synchronizer block, also the clock recovery MM. These are all included in the symbol sync block.
But I've seen
if
most of
you
the
look
use
at
for
the,
NFS and phase modulation, but in this case I found it in an example. I used it for FSK. But in essence, that's the same thing. You could use a block for everything where you have multiple samples per symbol, and it seems to find automatically and retune itself to find where exactly the mapping between the number of samples and the symbol.
but I think you still are dealing with a stream of symbols that have not been assembled into characters or bytes.
That's correct. But for that, I had my Python code that actually you could find out where to start. But because you also do you do the clock recovery yourself, and I wonder
the clock recovery and the byte assembly. Yeah. It's all in the Python code.
Both of these ways work just fine. There's probably trade-offs. There's probably some things that maybe the clock recovery block definitely has a lot of parameters. They are well documented in papers, but that doesn't mean that it's highly usable if you're just approaching it. And yeah, I mean, having it written out for this specific mode probably makes it simpler to read in the Python, but probably less computationally efficient.
If I can make a comment.
From what I read is that the clock recovery block has an internal phase lock loop, so it's probably much more complicated and much more robust for symbols that actually have a bad quality.
Marcus.
Yeah, hi. I'm just amazed by like how deep this discussion goes, and I'm basically wanting to say the same thing that Derek just said. Like, it usually depends. Like, there's a lot of trade-offs in here, and clearly, like clock recovery is like one of the things that are very specific to everything you specifically do with your system, right? You have some pulse shaping and day influence, how you figure out where your specific instant is, where you need to look and take the symbol value and say, oh, that's the symbol here. And so doing it differently for different systems is totally normal. So there's no wrong or right general way. I agree the symbol synchronizer block is super awesome, and I think Andy Wall's, like most of that is Andy Wall's work, and he talked about that actually, and it's on the internet. Now I have to lie, that was at GRCon in San Diego.
It wasn't recorded.
Shoot. All right, that was the workshop. It wasn't recorded.
Okay, we have a subject for the next radio.
So I can't host that workshop. You have to convince Andy Walls to do that.
I might have a like back of the room recording of part of it, but no, we didn't record that officially. And we learned our lesson, and workshops are now recorded because it was excellent.
There are actually, I think, some slides, some PDF slides on the internet of Andy Wall's talk. Or perhaps some other talk.
So that's a bit my question. Have you heard those blogs which have those super ingenious people writing code who are doing, I don't know what kind of math?
Mostly
Probably
control
going to be
theory.
better than whatever I or somebody else writes in Python.
So-
in some blog that we just do 1, 2, 3, click, 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 and okay, kind of works with symbols that on our test. But if you use it, I guess on signals that have a bad signal to noise, that you will probably have a better result with the mathematically magical things.
So this is engineering, right? Nothing ever works perfectly. For very couple special cases, and this is what's so exciting about SDR for me, is like we can actually calculate, this is the best way to do it. And we do it that way, and we can prove it won't work better. But honestly, symbol recovery is kind of, if we can derive what's optimal in any case, then we're making a lot of assumptions about what happens between your transmitter and your receiver to the bits. So I wouldn't, say what I write is always worse than the magical block that someone with decades of experience writes, because what you might be writing is something that is matched to your use case. Parameterizing the great omnipotent recovery block might not be trivial. Like there might not be an easy solution to what is the right way to set this up. And it's totally reasonable to assume, okay, this is something that I can optimize later on, right? Do what works first. If you then have potential to optimize, do that by all means, get help, discuss things, but never be stopped by, my current approach isn't optimal. Like start.
Okay.
This is what my advisor tells me all the time. And that's, yeah, I should probably heed that.
But is it possible to have another workshop to explain clock recovery circuits? Because those are things that and I'm first to say dumb it down a little bit, because those are other things that interest me about these blocks.
I would recommend going to the tutorials and the one that calls second from the bottom in beginner user level, QPSK modulation, demodulation. And it's not easy, but if you work through that, you will have the clock recovery explained pretty well.
Barry, I think I tried reading that blog 3 or 4 times with that. Every
I
time
have a
it's-
suggestion. I have a suggestion to make. I found it really, really useful, and that is to check the GNU Radio API doxygen. So that's auto-generated documentation for the GNU Radio API. It's surprising how much information there is in both in the doxygen and in the actual code itself. It's something that I always do when I try to use something. I just go read the doxygen documentation. You can find it on the GNU Radio website, and then maybe also check the headers for each in the source code, because there's a lot of documentation, including algorithms. It's something that I always do when I try to do something. It's not in the weekend. It's not on the main website, but it's there. It's a lot of information.
There are several clock recovery blocks, as I recall, and one of the ones that was mentioned earlier, I think, has been deprecated. Marcus, do you know, was it M&M that was deprecated or one of the others?
Yes, you're right. Something was deprecated. I don't like. Zeef is like a very, nice word to describe my memories. I guess I can't remember which one was deprecated, but yes, there was deprecation in there. Like basically, mostly I think because things got condensed into the symbol synchronizer, but I really can't fully describe what was there. So sorry.
It was the equalizer I was remembering.
Oh, that was MMSE.
LMSDD has been deprecated, but the tutorial talks about it. Didn't use it, it just said that's another way of doing
Okay.
Well, shall we wrap it up for today? And I want to point out that on my user page there, in addition to the agenda, it shows where the chat room is. And also there is a page to leave comments about this session and thoughts about other sessions on the Talk Ham Radio wiki page. And there's a link for that there too. Let me double check that. Okay. Yeah, there are links for that on the bottom of the agenda page there. It says Talk Ham Radio. If you go to that, you can enter comments about this session, suggestions for other sessions, any other related stuff. And then the chat channel is listed there on the bottom if you haven't already been there. Okay. One thing I haven't been able to find again is the chat for this session. I know
There's no new messages.
there. Okay. Okay, I'm glad you're watching that because I had lost it. I've got so many places to look to see this various stuff. Okay, well, I thank all of you for coming and enjoyed doing it and look forward to your comments on the wiki and the chat page.
Thank you.
Appreciate your time, guys.
Bye. Thanks.
Thank you. Thank you. Bye.
7-3.
Thanks, Barry.
7-3.
Okay, bye. Nate.